We have so far discussed about the strategic information, the need for online analytical processing, and the way the decision makers or the knowledge workers or the analysts are going to look at the information and how the information has to be present or has to be presented so that it is easier for them to gather insights that will help them in making the strategic decisions. And what we have seen that it's a multidimensional database is going to help in analysis, and it has some advantages with respect to analytical processing compared to relational databases. All through you would have noticed that there is some element that is required, that the entire information is available in the relational format, but we need to convert it into multidimensional or a cube format in order for the analysts to use the information. And let's look at how easy or how difficult it is to compute a cube. Now let's see. This applies, lattice applies to a retail chain. Let us say a retail chain has got several locations where they operate, and they sell a lot of items, and their items are supplied by many suppliers. And now they want to analyze how the sales are happening for various items at various points of time, at various locations, based on the various suppliers. So now let's see, as you may remember the analyst session that we had discussed in the previous session. They observe different things and want to keep moving from one perspective to another perspective, and that is quite ad hoc. So you can never tell upfront what is the way in which the analyst is going to analyze the data or look at them, and what is the kind of correlation that they will be looking in the information. So what that means is, in this situation, you need to compute the entire cube, because the analyst may go from the time of the supplier to the supplier's items they may want to go at the summarize at the supplier level, or they may look at the impact at the various locations for the same item. So what that means is that you cannot predict, and so what that means is that you need to compute all these cuboids. This is a way you may be able to represent all the cuboids that are required to compute the complete data cube, so that at the time of the analysis, you're not going back and doing a SQL query and then doing a sorting, group by, summation and all that, because then the session will become very slow. So now let's see how many summaries that you need to compute. So here there are 4 dimensions, and you can see one by one, and you can see that 1, 2, 3, 4, 5, and you're going to get 16 summaries are required. Here there are 3 dimensions, or rather 4 dimensions, and you require 16 summaries. And you may think, oh, what will happen if there are 5 dimensions? What will happen if there are 10 dimensions? And if you plot in this similar way, you're going to get the number. But let's give the formula. It is straight away 2 to the power of number of dimensions. So if you are calculating if you want to know how many summaries you need to calculate, in this case for 4 dimensions it is 16, and for 5 dimensions it is 2 to the power of 5, 32. If it is 10 dimensional analysis that you are doing, 2 to the power of 10, it is 1024. So the number of summaries is going in an exponential way. And now let's go one step further. It is not necessary that each dimension will have only one value or one level of values which is useful for analysis. For example, when they are analyzing the sales, they may be doing the analysis at a city level, or maybe at a lower level than that, or maybe at a country level, or they may be doing at a continent level. So what it means is there is a hierarchy that is associated with each dimension. So now let us take a different situation. So you still have again 4 dimensions, but let us say each dimension has 4 levels of hierarchy. So in that case, what will happen is that to make it clear to you, let's not take 4 and 4. Let us take, there are 4 dimensions, and then the hierarchy is at 2 levels. Okay, so that is to say the industry, category, product is becoming 3 levels. So let us say it is 3 levels of the hierarchy and the 4 dimensions. So then instead of doing 2 to the power of 4, you are going to do 3 plus 1 to the power of 4. So that is, it is 4 to the power of 4. So now what happens if the conceptual hierarchy for each dimension is going into 6 levels and you have got 10 dimensions? So the number of summaries that you require is 7 to the power of 10. So you can easily make out it is a huge effort on terms of the time, memory, and then storage, disk capacity, etc. to compute the entire cube and store it so that the analyst using any perspective and can go from one perspective to another perspective as they wish. So considering the cost of cube computation for a large databases with many dimensions, the researchers looked at the several ways in which it can be optimized so that you can compute the effective cube, not the complete cube, with much lesser cost. So first concept that we need to know is that the cube materialization. So that is to say, you may remember from the view materialization, it is always possible that you have a view either that exists as a logical definition, or you materialize the view, and so you pre-compute essentially the complete tabular structure for the view and store it, so that when you refer to the view, it is straight away accessed from the physical values that are available, rather than take the logical definition and go to the physical tables and recompute it. So we are talking in similar terms in terms of cube materialization. What are the things of values that we should calculate and store? So in this context, we need to understand the term iceberg cube. So if you know about, if you must have heard about icebergs. So the iceberg is generally, let's say it is there in the oceans, and the iceberg appears very small when you see from outside, but the size of the iceberg is much bigger than what it is. So the iceberg floats only to the 10% or 5% of the iceberg floats above water, but rest of it is below the water level. So only a small iceberg is visible at any time. So this is to say that's because the density of the ice is so close to the density of the water that it will not, the floating will be almost at the same level as the level of the water, and the density of the ice is slightly lower, so only a small part of the iceberg will be visible. So the concept is used because when you have, let's go to the example of the automobile manufacturer who is analyzing the sales based on the dealers, based on the products, and based on, let's say, the features of the product, let's say the color of the product. And let's take consider the situation. For example, there are numerous dealers who are available. There are 100 dealers that the automobile manufacturer has in the country. And let's say out of them 10 dealers are in cities and 90 dealers are in small towns. And also let us assume that in smaller town, the roads are generally narrow and people don't want to buy sedans because it is difficult to drive through. Let's take the example. So what that means is that the sales of the sedans generally happen only with the 10 dealers, though the other 90 dealers are present. but they seldom sell the sedan. So when the automobile manufacturer is analyzing the sales of the automobiles, they know pretty well that for sedan sales, they need to look at those 10 dealers who are going to sell them. For all others, it is going to come at 0. So it helps significantly if you realize that the significant analysis always happens with the larger numbers, not with the insignificant numbers. So even if one item is sold in some dealer for some region, they may not be of so much interest to the automobile manufacturer. So they're going to look at the values which have a significant support, which they, in data mining terminology, look at the support. So the saying that only if the transactions have a certain count, they're of interest to us to do the carry out the further analysis. So if they sell one item in a year at one particular place, they don't want to bother too much because they just want to still may facilitate the sale, but they don't want to analyze that much further. So now to identify, if you think that you want to calculate the cube, materialize the cube only based on the support. So unless there is a certain value in that cuboid, you don't want to consider the calculation. So that is, you never calculate the summary. If you know that for a particular dealer, for a particular model, the sales are not going to happen because for that dealer, the overall sales itself is small or something of that kind. So for example, in a grocery store, there may be 1,000 items, but there will be some items which are fast moving. So they sell thousands of items in a day. But there will be items which they sell once in a week, but they still stock them because they don't want to disappoint the customers who come for that item. But the grocery chain may not be so much interested in analyzing such sales. So now let's look at an extreme situation. So you have a database where there is the dimensional model which has 100 dimensions. But what you notice is that there are only 2 base cells with respect to those dimensions. So there are only at the dimensions, there are only 2 combinations which have got a values. So that is saying that A1 to A100, that is, let us say that is one record, and then B1 to B100, that is representing again the 100 dimensions, that is another record. Now let's look at how many aggregate cells we will have if we are accepting when the count is equal to 1. So here it is to the order of 2 to the power of 100 aggregates that you will compute if you say that the support of 1 is sufficient for you to take interest in this thus aggregates. Now let's say that we want to look at the aggregates only if they have a support level of 2 or more. So that is only if the aggregate value is 2 or more, you want to look at that. So now considering these dimensions, that each dimension value is completely different. So for the first dimension, first record has a value of A1, the second record has a value of B1. So now what is happening is that once you look at it, there is not a single aggregate cell which has a support of 2 or more. So there is nothing of interest to you. So you can see the significant difference that support level has made to the calculation. This is an extreme example just to clarify that the support level can make a significant difference. But in other cases also there will be, you can get a significant performance advantage by identifying a support level. Now here is another situation which we want to understand. There may be numerous aggregates that they come up because, as we have seen, when you are looking at a lattice of cuboids, each hierarchy is representing, for example, you are looking at the sale by item, and the sale by item can be divided by sale by supplier. So the supplier 1, supplier 2, they are there for the item 1. So item 1, supplier 1, item 1, supplier 2. So the thing is that these are closely related aggregates. Then if you look at them, if you look at a different situation here, you've got a 2 base cells representing again 100 dimensions. So in the first case, you have got a value of 10, And in other case, you got a value of 10. But what you can see is that the dimensions have some overlap. First two dimensions, A1 and A2, you can see that the same dimensions are repeated, same values are repeating, and then the other dimensions have a different value. So now here, if you're again looking at the distinct aggregates that you're going to get, you are going to get 2 to the power of 101 distinct aggregates about. And that will be, and when you look at them, you're going to get a value like this. So if you start replacing some of the values which are insignificant, though whatever be the value, you're going to get the same. So if you have got a more effective representation, then you will realize that you are not getting much of new information if you scan through 2 to the power of 101. So if you and in fact, if you want to know the interesting information which is providing you some value, you can see that there are only 3 distinct representations that are sufficient to get all the interesting values. So that is, first one is 10 when A1 to 100. Another one is A1, A2, and then up to B1, B3 to B100, that is 10. And another one is with A1 and A2, irrespective of the other values, you are getting 20. There are 3 interesting values that you are noticing. All others can be easily derived from this, because looking at those stars, you can see that if you represent this with the as a one record by using a suitable notation, you do not require any other record. So the 2 to the power of 100 or distinct aggregates are almost all of them are trivial for the purpose of analysis. So if you know these concepts, then possibly you better understand why there are some of these techniques are being used to improve the cube computation. So some of the general strategies that apply for the data cube computation for the purpose of optimizing the complexity involved, the complexity both with respect to the time and space. So the sorting, hashing, and grouping are done first. And if you can effectively use the sorting, hashing, and grouping, you're going to get significant performance advantage. For the simple reason that if you can sort them, you're going to get the values of the particular dimension together. So at that point of time, a single scan or a single page access is going to get you the significant number of records related to the same dimension, or the adjacent pages are going to give, or in any case, at some point in the sort, if it is sorted, it is easier to realize once when you stop taking interest further. I mean, you don't need to scan the entire table. You only scan from, let's say, 1024 to 1076. Those are the records that are of importance for this dimension. So the sorting and using the appropriate sorting for calculating the aggregate is going to significantly improve the performance. As you're looking at the example, so if you're doing the branch, day, item summaries, so it will help significantly if you can sort the tuples by branch followed by day and then group them by item. And similarly, if considering that most of these servers come with the multiprocessing capabilities, and they have the ability to run the simultaneous processing, and many of these data warehouse or the OLAP solutions are the smart enough solutions that they can parallelize the operations in order to get the benefit of the multiprocessing systems. So there is an opportunity for simultaneous aggregations in several situations. For example, you want to look at the item, and you have got the item and the supplier. So you can consider that as you are doing the supplier aggregation, you are doing the item aggregation for the supplier, and at the same time you are also doing the aggregation for the another purpose, that is the item aggregation itself. So there are always possible to think in terms of calculating the higher level aggregates based on the lower level aggregates. And then there is another way you can optimize. For example, you are thinking in terms of calculating the summary for a branch. So you may be already having the summary for the branch for the year, or you may be having the summary for the branch per item. So you may be realizing that there are 5 years of data that is available and there are 1,000 items that the branch deals with. So you clearly know that if you go by the summary of the branch per year, then it is much easier to calculate the summary for the branch rather than going through the path of summary of the branch and item. And there is another technique that you may use, which is a independent technique, which is, for example, the a priori pruning. Now let's say that you are calculating the cubes, and you have noticed that, and let us say you are not using the previously mentioned aggregation techniques where you are calculating the higher level aggregates from lower level aggregates, but you are calculating the other way around. You started calculating the higher level aggregates, and then you realize, for example, that the support level that you want for calculating the aggregates is that 100. And then you realize that the total sale of sedans by the manufacturer for the particular month is 95. Then you know that you don't have to calculate any of the other lower level aggregates, that is to say, for this dealer for that month how many sedans were sold, for this dealer of this color how many sedans were sold. You don't need that at all, because the overall sedan numbers is not meeting the support level that is required for the Iceberg cube, which the analyst considers sufficient for the purpose of analysis. So if we use all these optimization techniques, we will be getting a significant benefit with respect to both the cost and time for the data cube computation. Thank you.